Okay, this week we're going to talk about thunderstorms. I love to watch thunderstorms, uh, and particularly to try to understand them. There is so much I don't understand about them. We're going to talk about some of the basics today, some of the things I actually do understand, and hopefully I can get across to you all. So, what conditions in the atmosphere favor the development of convection? Basically, a thunderstorm. So, we'll start with that premise and work our way forward. There have been numerous outbreaks over the years, but let's just look at a thunderstorm right now. The first thing you can see if you ever look outside when they begin to develop is a developing cumulus cloud, a towering cumulus cloud. And all the air in that cloud initially is going upwards. There's nothing going down. Eventually, you get so much air up there that the weight of that air, precipitation begins to fall out of that cloud. Precipitation will cool that part of the cloud because of evaporation of that water, even as it's precipitating. So you wind up with a downdraft where the stable air is. So you wind up with an updraft in the front and downdraft behind. So this front thunderstorm will be moving from the right side to the left side. And finally, at the end, pretty much everything's going down in the bottom of the thunderstorm. There's just some clouds left. So if you were to look at any given thunderstorm, this is the process that happens. Each one of these phases occurs. Now, thunderstorms have to start from somewhere. So they have a couple of options. One is free convection. It's kind of rare, but it does happen, particularly in the summertime where pure heating triggers an updraft of thunderstorms. The air gets unstable enough and just gradually goes up, and you begin that initial cumulus cloud, towering cumulus, and then moving on to a thunderstorm. But most of the time, there's a front or orographic lift or winds converging, maybe from a sea breeze. But there's some kind of convergence. When that happens, the lift begins, and what happens is it eventually hits saturation. Saturation releases latent heat. Then the instability kicks in, and you wind up with just what we talked about, that thunderstorm. So now that we've talked about the various stages of it, let's move on down to classifications of it. So in the summertime, most of the thunderstorms are single cell. However, there are times when multi-cell clusters or multi-cell lines form. And a couple things go into making a thunderstorm. Obviously, they need instability. The more instability, the stronger the updraft is going to be. But there's another factor. You want to keep that updraft going. And wind shear is what causes the updraft going. So if we talk about wind shear, we talk about winds changing direction with height. So take a look at this today's sounding here. We have winds out of the south at this location. Then they turn to the southwest at 30 knots and gradually become weaker, but they're more out of the west. So there's actually wind shear occurring in the lowest levels. And with that, the wind shear causes the outflow that develops to not be able to push out ahead of that updraft. So what happens is the updraft is able to sustain itself. New updrafts may develop, and you wind up with a cluster of thunderstorms. Back to where we were. So you wind up with this multi-cell cluster or multi-cell line. Now, if you have really strong wind shear, typically the wind shear has got to be at least 40 knots in the lowest 6 kilometers of the atmosphere. Typically, it's more like 60 knots or more for a supercell to form. And that's where rotation develops in the thunderstorm. They have tremendous updrafts. And those are the ones that cause a vast majority of the severe weather. However, multi-cell and multi-cell clusters and lines both can cause severe weather. Single cells, there's a very slight chance you might get a downburst out of one that might cause severe weather, but it is not likely. So these are the four classifications or groups of thunderstorms. Single cell, one cell goes up, dies, comes back down. Multi-cell, well, multi-cell is a little different. You can actually see that here. What happens is there's a new thunderstorm developing, continues to develop along this at different phases here until the top one here is dissipating. The thunderstorms are actually moving to the northeast. However, because the new cells are always forming at the southernmost part of that line, or that grouping of thunderstorms, if you live up here somewhere, you might get 1, 2 thunderstorms that went over your house instead of just one, so you get longer-lived thunderstorms. And the actual motion of the cluster of thunderstorms is to the east. So you can see here, you have to take into account the new cells forming and the direction of the motion of the thunderstorms themselves. So multi-cell or mesoscale convective complexes, or squall lines many times called, are very much where you have several cells in various stages going over your house. So the conditions to get these supercells, many times there's thunderstorms. One of the questions you're going to get asked is, why is Florida so thunderstorm prone? Because it has the highest frequency of thunderstorms in the United States. Think about it. It's fairly tropical. It has a lot of maritime tropical air over it. And you have sea breezes on both the Gulf Coast and the Atlantic coast. And when they hit together, you have convergence. And what winds up happening? You get a line of thunderstorms in the middle there. So, with that, here is a classic example of when you get tornadoes. You have a low-level wind jet. This is probably about 4,000 to 5,000 feet up. You have a higher level jet, maybe at 15,000 to 20,000 feet up. Notice one is coming out of the southeast and one's coming out of the southwest. They're very strong wind shear in there. You have lots of maritime tropical air in here. Here you might have some continental tropical air. So let's take a look back at that sounding. I think I got it here somewhere. Yeah. So I have maritime tropical air down here. This green line is going to be more over here, very much next to the red line. So you're going to wind up with a lot of moisture, not quite saturated, but pretty close, moving upwards. Here, on the other hand, you're going to be very dry. And then maybe above that, maybe some more moisture coming in. So what happens in this area where it's very dry, very warm, temperatures are over here somewhere maybe, but they're very dry. All this moisture comes up, being lifted up by the convection, by the convergence of that front. When it's lifted up, it's hitting that dry air and it's evaporating. So that temperature that was way over here maybe is now moved back further and further to the colder side. So that air, warm, nice, moist air parcel that was lifted from down here near the ground has a much warmer temperature than its surrounding. So it's going to accelerate upwards. You combine that with the wind shear and you get a tremendous updraft, maybe over 100 to 150 mile an hour sometimes. So that's how these tornadoes get developed in these kind of a system. And here you can actually see just talking about that. One of the things you want is more sunshine. The hotter the air gets, obviously the stronger the convection could become. Lightning is a byproduct of a thunderstorm. So with that, at temperatures less than 5 degrees, graupel, which is kind of a liquid ice, kind of like almost a sleet kind of a particle, It's a group. It's made up of a series of ice and liquid. It's kind of partially frozen together. They become negatively charged. Pure ice crystals, on the other hand, become positively charged. Now, the temperature is greater than 5 degrees. Positive charge happens to the grapple, a negative charge to the ice crystals. So if you look at that in a thunderstorm, down here in the low level, you have one set of charges. In the upper level, you have a flip of the charges. So you wind up with this updraft causing all these charges to separate, and you wind up with a very powerful charge in a storm. You get negative charge coming down towards the ground, try to hit the ground, and eventually a whole big positive charge going back up into the cloud on cloud-to-ground lightning. So that's how your lightning forms. Because grapple and ice crystals change their charge with height, with temperatures, and with the tremendous updraft to pull them apart and separate them, you wind up with very different charges in different parts of the storm. And one thing to know, lightning can come out of the anvil up here. It can actually strike over 15 to 20 miles away from the storm. So if you're ever outside and see a pretty anvil, but you're not seeing the real dark cloud, you still need to be conscious that lightning could occur. And take a look at that right now, what's going on in the U.S. This is a lightning mapper. So the redder the image, the more the lightnings are striking. If you look down here in Tennessee, border of North Carolina, you see lots of lightning. There's some along the immediate coastline here. There's even a little bit around Hurricane Hannah. Not a lot. So you can see lightning even, out here in the mountains, in the Rocky Mountain area, there's some lightning. So lightning's pretty popular today around the country. More intense lightning is along these areas. So again, another thing to think about with thunderstorms, I wanted to show a little bit, is there's something called moisture convergence. Moisture convergence is basically converging air, and it's bringing in tons of moisture with it. So what that is providing is, looking at the lower level of the atmosphere, you're seeing moisture come together, and you're seeing uplift being caused. The stronger these are, the more the uplift. And many times you can look for moisture convergence before the actual thunderstorms form. If you look here right along the coastline, you're seeing moisture convergence. We saw a lot of lightning down there. There's some also happening in the Gulf of Mexico down here. Oh yeah, there's a lot with Hurricane Hannah. So that's just one of the aspects. Another thing, we talked about stability, and here's some of the instability. These are products called CAPE, convective available potential energy. The larger the value is, the more uplift potential there is. Here's 2,500. Here's 2,500 over here. There's 2,500 back here. So there's a lot of potential for lift down here. Anything above 1,000 is fairly high. When it gets some of the severe weather, you may get upwards of 5,000 of these. So this is really a good example of looking at where the convection, you saw the moisture convergence, you see in the convection. So moving along here quickly now, downbursts occur all over with any thunderstorm. Think about all that air that went up, all of it's got to come down at some point. When it hits the ground, it just diverges. It can't go into the ground. So it may go in different directions. And these are extremely dangerous at airports, because as the plane flies into them, it's getting a headwind that might help it rise. When it flies out of it, it's getting a tailwind. It's going to help it sink down. So aircraft have to be aware of these. So a lot of the airports have what they call terminal Doppler radars, which actually work fairly close to the ground and try to spot these before an aircraft flies into one. They try to catch it so that the aircraft won't hit to that danger zone. Derechos are just long-lived wind events. Obviously, if you get a lot of convection and mesoscale convective complexes form, and if they don't move a whole lot, you can get flash flooding. tremendous amounts of rainfall occur in these storms. Hail is another hazard that happens with thunderstorms and the different sizes of hail. Hail begins in the upper part of the cloud where moisture is being pushed up and freezing. It allows it, gets out of the updraft, starts sinking back down, gets pushed back up, and gradually develops in this higher level of cloud. Eventually it gets too heavy, it starts sinking down, and eventually it will hit the ground. This hail in the dual pole radar, which we talked about the other week, is where you can pick that up and actually see it form in the cloud, and you can watch it sink, and you can actually give warnings to the public based on that. So with that, here is actually what they call multi-sensor, multi-radar image. There's a bunch of algorithms here that are trying to detect things like rotation, hail, where lightning will occur, where reflectivity may be changing. You'll notice a couple rotational tracks right here just south of Houston. If you look at Hannah, just south of Houston, there's some pretty powerful thunderstorms on one of their outer bands there. And that's an area where potential tornadoes could develop today, in the next few hours, actually. You can actually see a small eye developed right there, and then it's beginning to close up again as it hit land. So that's when the storm probably reached its maximum intensity. So that's about what I have here. So if you have any questions about thunderstorms, please feel free to ask. Enjoy the weather this week.